So we have covered a lot already, and today I'll be, as I said, finishing off more questions, practice questions, and information that you require. So we are almost. It does go till 20.5, but then 20 point up to 20.3 is the main teaching component. 20.4 is a core practical discussion, and 20.5 is again a bunch of lab related. So 20.4 and 5 is more connected to your unit 6, the practical exam situation. Okay, so let's have a look at our where we left off last time. So we were doing some practice questions on organic synthesis. We were trying to convert one compound into the other. And last time, if you could just make sure that you have your last class notes with you and your organic notes with you, including the previous unit's organic notes. That's always a good idea if you have them around with you. Of course, so you can refer them. And as we're going to discuss more questions today, practice questions today, you'll get a chance to revise all the older organic portions also, which all are going to be a part of these lessons discussions. Okay. Once again, remember the main idea in 20.3 is to convert with the information that you already know, familiar compounds. You use that information and try to figure out the unfamiliar compounds synthesis. Okay, so picking up some, we are, I think, still going on at 20.3. And we are discussing synthesis examples. Okay, so what we did, just to give you, last time we started with benzene, we looked at your A level components, we looked at your AS level, the open chain, alkanes, alkenes, how to convert from them. Okay, how to, and we're going to pay attention today's class, particularly how to increase the number of carbon in the chain. So that's another, and especially the new thing which is called the Grignard reagent, and what is it used for, and how do I use that to figure out the preparation of certain special compounds which has been mentioned. Okay, let's do an example question there. For example, if I want to convert, let's say I want to start with benzene. This is the worst case scenario. An examiner says, I want you to change benzene into, let's say, this. I want to put a methyl group here. I want to put a nitro group here. So this is like 4 nitro methyl benzene. So what I'm going to do is I'm going to give you maybe a minute to think. Now, using your previous class knowledge, this is just a recall question. These are not application questions. I know it's synthesis, but then, as I said before, it's almost everything is based on recall. So you need to remember, how do I put the nitro on the ring? How do I put the methyl on the ring? Now, there is something special I also want to tell you today. Okay, so this is important. This is some additional information which could be very useful for you. Now, groups like, there are two information I want to put, okay? So I wanted to use this information, although it is not specifically mentioned, but you'll find it very useful. For groups like, okay, groups like any R group. So when I say R group, I'm talking of methyl, or I'm talking of ethyl, etc. Or OH or NH2. Okay, if you have any of these groups already on the benzene ring, okay, so they influence, okay, let me write it in a very simplified way. They influence the incoming second incoming group at position. You'll find this very useful at position 2, 4, or 6. Okay, so what I'm trying to say is, if already there is a methyl group or a OH group or a NH2 group in the benzene ring, and you want to put something else in the benzene ring, that second group that you want to put, it's going to go at position 2, 4, 6. You don't need to know the detail of it. They are basically called as ortho-para directing groups. You might have heard of this before. So ortho means position 1, 2, para means position 1, 4, Okay, so this is ortho and para directing groups. So these groups, and I'm just writing just a group that you really have to be worried about. So that's for rule number A. And there is also for B, there are certain groups who does something else. Groups like, and I'm giving the groups that you are dealing with. Okay, so carboxylic acid is there, nitro is there. Okay, it can even be a CO, well, amide group is there. Let's say a COR group is there, etc. They influence. So what happens is, when if any of these is already present, they influence the second group who is coming, second group which is incoming to position 3. Okay, so these are called meta directing. Okay, so this is very good information for you, and you might find it when you look at the past paper question. The examiners have used this rule actually. So these are called meta directing. Meta directing. So, not metal, sorry. So meta directing. Meta means position 1 comma 3. So 1 is already at nitro or acid, or somebody is already at position 1. The next one comes at position 3. So I don't know why I'm constantly writing metal here for some reason. So this is the referred as the meta position there. Okay. And then these which are influencing the group 2 position 2, 4, 6, these are called para directing. Para directing. Para means position 1, 2, and position 1, 4. They're called para positions. Ortho and para position, right? Ortho means, sorry, ortho is 1, 2, and para is 1, 4. Meta is 1, 3. So meta is 1, 3. Okay, maybe if you want, just make a note. If it's 1 and 2, we call it ortho. If position 1 and 3, we call it meta. And if it's position 1 and 4, we call it para. Okay, so these are some additional information which you'll find it very useful. Now, for example, if you look at this question which I gave you, now this is good for you, although it's an exam question for you, but it makes sense to you and it gives you an idea which group should you put first in the ring. Like, should I put methyl on the ring first, or should I put the nitro on the ring? So this is where these information comes very handy. If you're going to put nitro on the ring, the problem is nitro is a meta directing group. It means after putting nitro, if you want to bring the methyl is going to go to position 3. But the way I gave the structure, methyl at position 1, nitro at position 4. Which means this gives you an idea. The first thing you want to put in the benzene has to be the methyl group, because methyl group is the para directing group. So if I put methyl first, then nitro is going to go to position 4. It will not go to, like, I can bring nitro to position 2. I can bring nitro here. I can bring nitro here. I can bring nitro here if I put methyl first. Okay, have you understood the idea? So it's a very useful information that you can use in this lesson. Okay, so just remember these 2 points which I wrote, that will help you out in any situation. Okay, so which means now I want to change benzene into 4 nitro methyl benzene. So now you understood the first thing that you have to do is you have to put the methyl group in the benzene ring. So I'm sure you know what to do. So, okay, do you have any suggestions? How do I put methyl group in the benzene ring? Who should be my reagent? Like, what should be my step 1? I have to react. Remember Friedel-Crafts alkylation? We did that in the, I think, in the beginning in topic 18. Friedel-Crafts alkylation we did. Friedel-Crafts acylation we did. So I want to put CH3 in it. Guys, give me yes or no if you remember Friedel-Crafts alkylation. If you just open your topic 18 notes, you will find it there. So who should be the reagent I said, look at the group which is on the ring. I need CH3 on the ring. So my reagent has to be CH3Cl. And then if you remember, what was the catalyst required? Very good. What was the catalyst required in alkylation? Just check the note. This is based on recall, as I said. So catalyst is AlCl3. Then I also said it's always good to know the name of the reaction, because these are all information that you should know. And I told you a simple way to keep in mind is anything that goes on the benzene ring is technically called as electrophilic substitution. Of course, you can say Friedel-Crafts alkylation, but that is just to honor the name of the scientist who made it. But the idea is the mechanism name. The reaction mechanism name is always the preferred name that you should use. So I'm just going to say this is electrophilic substitution. I'm just writing everything here. So it's like a revision for you. So this is electrophilic substitution. Remember, anything going on the benzene ring is always ES, electrophilic substitution. Okay, just for your reference, I'm also writing this is alkylation. So you could refer the notes. And then what happens? I get my methyl benzene. I'm not interested in the secondary products, but if you want, of course, you know HCl is going to be produced. So I got my methyl benzene. Okay, now what do I do? Anyone has a suggestion? I got my methyl benzene. What should be my next step? What should be my next step? What do I react this with? Or can you tell me what could be the name of the reaction at least? Write the name of the reaction in the Zoom chat. That will be easy for you. If you know the name of the reaction, it means you know the reaction. I need to put the nitro in the benzene ring. I need to put the nitro in the benzene ring. So if I have to put the nitro in the benzene ring, what do I need? I have to do nitration, correct? So what is my reagent? Concentrated. Yeah, so don't forget, it has to be concentrated HNO3. But then who should be the catalyst for this reaction? Whenever we do nitration, there is a special catalyst required. And the catalyst is concentrated H2SO4. This is the catalyst. And of course, I need heat 50 degrees Celsius to 60 degrees Celsius. Okay. This now again, I'm putting nitro on the benzene ring. So my correct way of naming this reaction is I'm going to still call it electrophilic substitution. Okay, so that's the key word I'm just putting in the bracket, electrophilic substitution, because sometimes you might say, okay, electrophilic. Uh, Examiner might say, okay, we'll give you mark even if you just say substitution. But which kind of substitution? So, sometimes they'll put that word electrophilic, nucleophilic in the bracket. So my advice always remains that just write the whole name, why you want to take a chance. So electrophilic substitution, right? It's also called as nitration, but that's a common name. That's not the reaction mechanism name. So I'm not a big fan of that. Okay, and then we do all that. And then just now I taught you that methyl group is a orthopara directing group. Orthopara directing group means methyl is going to force the second group who is coming either at position 2 or at position 4 or position 6. It's a very useful thing to know. So now you know that's the reason why nitro is going at position 4. See, extra detail you don't need to know, but it's all because of the orthopara directing groups. They kind of increase the electron density at these positions. So therefore, the electrophile finds it very easy to connect to these positions. Right, so that's about it. And yes, we will get secondary products H2O, but that is not our main concern. Remember, you will be only asked to convert this into some kind of a schematic flow, and that's about it. Two steps. We changed benzene to 4-nitro methyl benzene. Okay, so let's do another one parallel. Remember, we are still doing questions today, and I'm deliberately giving you a lot of questions so that you have a lot of information, particularly from even the older AS portions. So you have everything in one place. So when you study these notes, you can kind of memorize all of that, and It makes your life so much more easier when you do organic synthesis past paper questions. Okay, that reminds me, I hope your transition metals elements past papers are kind of ready. And yes, as promised, I will send you the remaining marking scheme also. Moving on to another question. For example, if I say now on the same lines, another very popular area is I want to change benzene to, let's say I want to change this into this. Now this is 3-chlorobenzoic acid. Okay, so I want to change benzene into 3-chlorobenzoic acid. So now you have to think. Okay, let me give you a minute for you to think. Maybe you want to make some kind of an idea in your mind, and maybe after a minute I'll start talking. Or mention R for ready if you think you have some idea how to do this. Well, that's basically a schematic flow which I made for you, just to help you out. Because this could be another format in the exams. What the teachers will take, they'll give you some in between steps as A, B, C, whatever, and they'll ask you to figure this out. So that also tells you how to do this. Now, remember what I said. One of the very good skills that you want to use is maybe you can work backward. Okay, that probably might be easier. Okay, so you see there is a carboxylic group and you see there is a chlorine group. Okay, so and then you want to go back on this notes which I wrote here, particularly if you look at the note for B, what I wrote here, groups like carboxylic, they influence the second group coming to position 3. So that's now hint for you. Now you know, probably, do you want to put the chlorine first on the ring or do you want to put the acid on the ring? So can you tell me what could be the structure of B? Like working backward, what could be the structure of B then? Like should I copy the same structure? This is 3-chlorobenzoic acid. Any suggestion? You can write the name of the compound if you want. Any suggestion? What could be the structure of B? Like from B, I should be able to get that. And look at this point again. The carboxylic acid influenced the second group coming to position 3. So any idea what this could be? So does that make sense to you that B could be this? Give me yes or no. Does that make sense to you that probably B should be something having the acid because the chlorine can come later? Give me Y for yes and for no if you're okay so far. We're just trying to understand how do we work this backward. Guys, give me yes or no in the Zoom chat, please. Okay. Now, if this is B, now this is something good for you. If you want to understand how do I put a carboxylic onto the benzene ring, so what could be the structure of A then? In that situation, if you remember some previous information, that if I want a carboxylic on the benzene ring, so which means I should be having a CH3 on the benzene ring prior to that. So that's the basically how we figure this out. So what's the final answer then? Now, this is like step 1 and this is step 2 and that is step 3. So basically it's a 3-step answer. So what is happening in step 1? In step 1, who should be the reagent and conditions? So this is the expected format. So what is this reagent condition? How do I put the CH3 on the benzene ring? We just now did one question on that. Do you remember? Reagent condition. What do I need to put the CH3 on the benzene ring? If you just look at our previous page, we did the first step there. So if I want to put the CH3, so I need my reagent as CH3Cl, correct? And then, okay, just give me a second, guys. Yes, honey. No, one which is next to the cloth shop where we give the clothes for the press and iron. Right next to it. That is correct. So that's my reagent CHCl3, and I will use AlCl3 catalyst, and I will also need heat, and this reaction is referred as electrophilic. I'm just writing the name of reactions wherever so that everything is in one place for you to learn. Okay, so electrophilic substitution, also referred as alkylation, Friedel-Crafts alkylation. Okay, good. All that done. Now in step two, so how do I change CH3 on the ring to carboxylic acid? Name of this reaction. This reaction is now referred as oxidation reaction. So the reagent plus conditions, well, I don't have to write it every time. So the reagent, what I need is I need KMNO4 acidified. Normally, when we say acidified, that is we normally use dilute H2SO4 in it. Okay, so that's what is used for acidification, and we also need to heat it. And this reaction is actually called as oxidation reaction. So the ethyl group on the benzene ring is getting oxidized. As you see, the hydrogen is being kicked out and the oxygen is being coming in. So that's basically oxidation going on. So that's step two. So how do I do step three? How do I put a chlorine on the benzene ring? You did this before at the beginning of topic 18. We did bromination and chlorination of benzene. So we know the reagent conditions. We did the mechanism of that as well, right? So how do I do that? So who's my reagent here? My reagent is chlorine, correct? And AlCl3 was the catalyst. We didn't require any heat, and the name of the reaction was electrophilic substitution because we put something in the benzene ring, so we call it electrophilic substitution there. Okay, I'm done. I'm waiting for your question. So examples of how to change benzene into 3-chlorobenzoic acid. Any questions at this point of time? Just if you have any questions, let me know, or if you're okay, just can you just type NQ? Everyone is okay. 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 The next thing what we are doing is we are now listing the different ways of how actually to increase the carbon length of the compound. Okay. So this is extending. So I'm just listing out everything. So again, makes it easy reference for you. Extending a carbon chain. Because when you do synthesis question, there will be so many times where you will be expected to know this, like how do I add one more carbon to the chain, like how do I do that? Okay, so here's the thing. So these are the four options. Three of them you already know. The fourth one is going to be something new which you have not done before. So the first way is if you do the reaction between reaction of halogen alkane. So you need a halogen alkane with KCN, not HCN. Remember, HCN is for aldehydes and ketones. So be careful. Reaction of halogen alkane with KCN in ethanol, not aqueous. Okay. So this, and then you will do heat under reflux. Because heat under reflux particularly is done for, as I told you before, compounds which are highly volatile, halogen alkanes, alcohols, they're all very volatile compounds. So wherever they are involved, you'll always find heat under reflux. You could, as I said, you could look it up in the Google. How does the apparatus look like? It's also given the end in your textbook as well. Okay, so heat under reflux. You can't just simply heat them in a beaker. That's not a good idea. You want to heat them under reflux conditions. Idea is to remember, this is done to ensure there is no loss of reactants because they are volatile, and you also want to ensure that the reaction goes to completion. In case they ask you, I'll just write a small comment here to prevent. I think I should write it, to prevent loss of reactants by evaporation. So that's one of the reasons why they do that. Second one is to ensure the reaction goes to completion. Reaction goes to completion. You just want to make sure that because it's a closed container, it just kind of recycles unreacted components till everything is not done. Okay, so that is one way to do it. Of course, I will give you example. If you want, I can give you a small example there. For example, I have a CH3CH2Cl, and if I react this with KCN, okay, don't forget it has KCN is not aqueous, it's alcoholic. Okay, so what happens now is a nucleophilic substitution, right? So now this Cn is going to come here and this Cl is out. So what you get now is CH3, CH2, Cn. And if you notice, I got one extra carbon. That was the entire story, okay? So what's happening now, that this is chloroethane, and it had two carbons. Now I have propane nitrile, and propane nitrile has three carbons. You see, one carbon got increased. Is everyone okay with it? You understood how to increase one carbon? Remember, you have to, I told you the whole organic synthesis is based on your ability to recall. So you got to memorize all of this. So KCN in alcohol conditions, heat under reflux, can give you one extra carbon. So this is one way to do it. Everyone okay with it? Give me Y for yes and for no. Okay. The second way is this is a reaction of carbonyl compound. Now, what is carbonyl compounds? This is all, actually these points are from your AS portions actually, so they're good information. When I say carbonyl compounds, I'm talking of aldehydes and ketones. So you can take a carbonyl compound and HCN. This is where the HCN comes in, hydrogen cyanide. Okay, and the catalyst is KCN. So KCN is the catalyst in this reaction. Catalyst is KCN and it is in aqueous condition. So this is in aqueous condition now, okay? Earlier, the KCN was dissolved in alcohol. Here, HCN is just simply in aqueous conditions. And we also need heat. And this reaction, I forgot to write the name. So the name of this reaction, this is nucleophilic substitution. Nucleophilic substitution, if they ask you the reaction name. Okay, and this also, this reaction is called nucleophilic addition. Nucleophilic addition. Good to know the name of every reaction which I'm discussing. Okay, remember, one of the best things for you to become very strong in the organic chemistry is to learn RCN, reagent, condition, name, everywhere. Reagent, condition, name. Who's the reagent? What are you reacting with? What's the reaction conditions? What's the name of this reaction? Okay, so always keep memorizing that again and again till everything becomes perfect. So let's do an example if you want. I mean, this is just to give you a little bit clarity. So this you see is aldehyde. I'm sure you remember. This is ethanol. Okay, so if I'm going to react this with hydrogen cyanide, I'm just giving a reaction, one reaction just for you to recall. So what happens now that I get what is called as a hydroxynitrile. Look very carefully what happened. Okay, so what happens now that I get the H and I get the CN here. Okay, so if you just pay attention, that's the H and that's the CN. You see, that's how they get added up. The HCN gets added up. It's a nucleophilic addition. This is called hydroxynitrile. Okay, this is simply called as hydroxynitriles. Yes, you can give IUPAC name as well. If you want to give the IUPAC name, that's carbon number 1, that's carbon number 2, that's carbon number 3. Would you want to give the name of this compound? I have OH at the second position, so I'm going to call this as 2-hydroxy 2-hydroxy propane with the E, propane nitrile, 2-hydroxy propane nitrile. Okay, a very quick question for you. Give me yes or no. That do you think this compound can show optical activity? Does it have a chiral carbon? Give me yes or no very quickly in the Zoom chat. It has a chiral carbon. Good to know that. Well done. So that's the chiral carbon there. A chiral carbon is the one which is connected to 4 different atoms or groups. So that means this is going to show optical isomers possible. Remember enantiomers. Enantiomers. Compounds having chiral carbons who are not superimposable. They're called enantiomers, and the presence of enantiomers is a condition for optical activity. Optical activity means they can rotate the plane polarized light to the right or to the left. Okay, good. So that was one reaction with the aldehyde. Maybe I'll give you another reaction with a ketone, because remember carbonyl means aldehydes and ketones. So even ketones do this reaction. Okay, so let's have a look at another example of a ketone, very simple ketone. That's CH3C double bond O. I'm just opening up there. This the functional group. That's propane on. So it does the same reaction. So now you know what happens when OH goes on the top and CN goes down. That's it. Just memorize that way. There's nothing very fancy to it. But you're getting one extra carbon. I didn't notice, show you that. I have 2 carbons here. I have 3 carbons here. You see this? Et became prop. See? 3 carbon. Correct? So one more carbon I added. Here same I'm going to do. I have here prop. So now what happens? I'm going to get the hydroxynitriles. I will always get that. Okay, so just put OH on top and the CN down. That's it. OH on top and CN down. Okay, and yes, you can go ahead with the name. That's carbon number 1, carbon number 2, carbon number 3. So this is 2-hydroxy 2-hydroxy 2-methyl, because I have a methyl group also now. This is a functional group. This is a functional group. 2-hydroxy 2-methyl propane nitrile. There you go. Okay. Is everything okay? Does it have a chiral carbon? Do you think this compound can show optical activity? Give me Y for yes and for no, because this is always a question that keeps coming in for these kind of equations. What do you say? Atma says no. Is that agreed by everyone? So it has no chiral present. Good answer there. It has no chiral carbon. So no optical activity possible. So that was my second method. So you can do halogen alkane with KCN. You can do a carbonyl compound, which could be an aldehyde or it could be a ketone. That reaction is called nucleophilic addition. and you need hydrogen cyanide in the presence of KCN as catalyst. Okay, two ways finished. Let's do a third way. Is everyone okay so far? Like on a scale of 1 to 10. 10 means you're comfortable, you know what's happening. 1 means you know. Could you tell me what's your comfort level? Is everyone fine with what I'm teaching? Are you finding it difficult or it's okay? Like basically it's a recall situation. Everyone is okay? You sure? I'm only getting response from a couple of guys. Already there's less students today. Okay. The third one is alkylation. This you did recently. Alkylation of benzene. Even this gives you, isn't it? In fact, I opened up the class today with the help of an alkylation reaction. The Friedel-Crafts alkylation clearly helps you to add carbons onto the benzene ring. You can add 1 carbon, you can add 2 carbon, you can add 3 carbon. It depends on what you want to change, right? So alkylation. So who could be my reagent here? So reagent is RCl. Remember this RCl. For example, it could be like a CH3Cl. It could be CH3CH2Cl. It could be CH3CH2CH2Cl. It doesn't matter. I can just take any kind of R, 1 carbon if I want to put 2 carbons or 3 carbons. It depends on how many carbons I want to put onto the benzene ring. It makes it so easy. And don't forget, the catalyst in this reaction is the good old AlCl3. And then since I'm putting something into the benzene ring, don't forget the name of this reaction is electrophilic substitution. Okay, so that's electrophilic substitution because I'm going to put something on the benzene ring. Of course, it is called Friedel-Crafts alkylation. Correct? You've studied that way. So, I mean, you've done so many equations already. For example, the question says, I want you to change benzene into ethyl benzene. Okay, so I want ethyl benzene. So, what reagent do I need? Easy. I want to put a CH2, CH3. I want to add 2 more carbons. Benzene is like literally C6H6. I want here C6H5, CH2, CH3. This is basically 8 carbons. I want to add 2 extra carbons there. And I think you got the idea how this is going to go. So who's my reagent then? What reagent do I need? What catalyst? So the reagent is CH3CH2Cl. Catalyst is AlCl3. And of course, I also need a bit of heat. Okay, catalyst AlCl3, and I just normally we say reagent and conditions. So, okay. Anyone has any doubts, any questions? Everyone is okay. These are the 3 normal ones, what you've you have already studied in your previous sessions. Okay, are you okay so far? Is everyone okay so far? The fourth one is something completely new. Okay, you have not done this before, so again this needs special attention, and please let me know the moment you are not comfortable. So the fourth one is using Grignard reagent. Okay, so there are 2 things to it. First, you have to know how to make a Grignard reagent. What is it? How do I make it? And then how do I figure out which one do I need? So I'm going to give you like 3-4 case studies. So that will give you a very good idea how to figure this out. Okay. So let's see what exactly is a Grignard reagent. So first of all, it is prepared by reacting halogen alkane with magnesium in dry ether. First of all, this is how we make a Grignard reagent. Okay, now the halogen alkane, there's a little extra information for you. The most preferred halogen alkane, okay. So I'm going to give information step by step and then tell me if we need more clarification. So preferred halogen alkane is uh, bromoalkane. So basically, it's halogen bromide. Okay, so this is bromo alkane, and the reason why is due to longer CBr bond length. I'm sure you will connect this to this because it has the CBr bond length is much longer compared to the fluoro CF or the CCl chloro because bromine is a bigger atom, right? So the CBr bond is longer. So because it has a longer bond length, so needs lower energy to break. Does that make sense? Break than CF or CCl, etc. We don't take the iodo one because normally bromo one is the most stable common. Of course, the iodo one can also do the job because CI bond is even more longer. So you'll find that the bromo one is always the most preferred one to make a Grignard region in a normal situation. Okay, so that's the reason why, because much easier to work with the CBr bonds, more longer, easy to remember. Longer the bond, lower the activation energy required. Okay, and then another comment is like why dry ether. So I'm just giving you some small bits of information which could be converted into a 1 mark question here and there. Dry ether is used since the problem is like the water is actually going to react with um, the, uh, the reagents since water can react with the Grignard reagent being formed. So that's the issue. You want to keep the Grignard region completely dry. You don't want to bring water anywhere close to it, because the moment it is formed and you have water somewhere close to it, that's going to convert that into something else, and you don't want to do that. Okay, so that's the reason why dry ether is used. It basically makes sure there is absolutely no water. In fact, I don't know, you might have heard of dry cleaning of your clothes, correct? That's one of the components. The ether class compounds are basically used for dry cleaning of clothes. What do you think dry cleaning of clothes is? There is no water being used. Your clothes are being cleansed without being water being used, okay, with the help of these kind of solvents. You might have sensitive instruments like your watch when you give watch for service or your mobile phone for service. They are cleansed with alcohol or ether compound. You can't be putting water inside mobile phone or you watch inside the phone to clean it up, right? That's going to be ridiculous. It's going to spoil electrical systems there. So that's where these solvents comes handy, okay? Where you don't want the water, but you want something liquidish so to do the job. Okay, so that explains everything. And let's see how a simple reaction is done. So let's say this is my RBR. So let's say this is my bromo. I'm going to give you equations to make you understand how this works. I'm just giving the introduction now. Let's say that's my bromo alkane. Okay, so I'm going to react this with magnesium. I always need dry ether. Okay, so what I get is our MgBr. This is Grignard reagent. I know it. You may say, "Oh, this is nothing very fancy." Wait till you get questions. So you need to have this understanding. How do I figure out what should be the R? That's where the challenge is. So this is the Grignard reagent. Okay, very simple. This is just an outline of how it's done. Take a bromoalkane, react with. Now take bromoalkane as per the requirement. That's where you need to be focusing on what kind of R do I need. Okay, that's the only one challenge that, but again, I'll teach you a trick how to overcome that. So you react these two together, you get yourself a Grignard reagent. Okay, and this is the introduction page of how to make a Grignard reagent. Now I'm going to show you what reaction it does. Then I'm going to show you example under each category. So far, everyone is okay? Like you got the idea what is Grignard reagent? How does it work? So I'm just going to write this as RMGBR. Okay, I don't have to put the dashes in between, but just to give you an outline how this is made. So this is RMG. Normally you'll find in the textbooks is written as RMGX, or I mean, for our sake of discussions, I'm just going to go with BR. As I said, it's much easier to go with BR all the time. Don't forget X supposed to be halogen, which obviously technically I can use any halogen, but as I said, the most preferred one is this one, BR here. Okay, good. So far everyone is fine. So what we are going to do now is we are going to look at reactions of Grignard reagent, like how do we use it and how do I figure out which Grignard reagent do I need. Okay, this is a skill that you have to develop. It's not just based on recall. So I'm going to give you examples where you understand the trick, like how do I know what should be the R and how do I develop this equation there. Okay, so I'll give you example. They're very easy to learn, but of course you need to make sure that you're comfortable with the tricks. I'm going to give you a couple of more than one example under each category, and hopefully that's going to make sure that you're okay. All right, let's have a look at our the heading goes as uh, Grignard reactions. So reactions involving Grignard reagents. Okay, so let's see how it's done. There are four reactions actually you have to study to understand how this goes. Okay, so this is the first reaction. First reaction is reaction with CO2. Now, if I do the reaction with CO2, this is to produce carboxylic acids. So this is the memorizing part. Like if you want a carboxylic acid, you are supposed to react the Grignard reagent with CO2, then you will get the carboxylic acid. Okay, now what I'm going to do, I'm going to give you an example of a carboxylic acid that I want you to make using this particular technique. So for example, let's say to prepare, and then we will do some additional questions. To prepare, let's say I want to prepare 3-methyl butanoic acid. Now, what is 3-methyl butanoic acid? But means 4 carbon, correct? So this is basically 4 carbon. I'm just opening up this way so that's as easy for you to follow. So that's my carbon number 1. And then I have a CH3 here. So this is carbon number 1, carbon number 2, carbon number 3, and carbon number 4. So this is CH3, CH, CH2. Yes, of course I can write it in so many different ways. I can write this as CH3 2 CH COOH. Give me yes or no that you understand that why I wrote it like this, CH3 and put 2 in the bracket, because I see there are 2 CH3s connected to this, but it's still 4 carbon chain. It is still same 3-methyl butanoic. Just because I wrote it this way doesn't mean it's become propanoic. Okay, so don't misunderstand that. Okay, so this is a simplified structure so that you know what's happening. So this is the trick, okay, which I wanted to emphasize. This part here, this part here, this is coming from CO2, okay, and this part here, this is coming from the Grignard reagent. So this is how you're going to break the whole thing. And because I need a Grignard reagent who can give me that, tell me if it makes sense to you that I need CH3, CH3, CH2. I need this part from the Grignard region, correct? So I need a bromoalkane. So this bit is going to come from this compound. Give me yes or no if you understand that. Just put a Br next to that uh, carbon number 2. Please give me yes or no if you understood. How do I know which bromoalkane I have to take? You you have you understood? Your starting bromoalkane is your starting bromoalkane is this, which is 1, 2, 3. This is, my dear children, 2 methyl. I'm sorry. This is 1 bromo because alphabetical sequence now. So this is 1 bromo, 2 methyl propane. Could you just tell me on a scale of 1 to 10, like how are you comfortable in what I'm talking? Everyone, could you just mention 1 to 10? Where are you on this one? Like, how do you know which bromoalkane I have to take? Everyone is okay? Very good. Dania, what about you? You're okay? Yeah? Okay. So, great. So you just break it here. So now that's easy, right? The COH coming from CO2, rest all jing bang is coming from there. And then I know I need to react. So first step is, see this, there are two steps to it. Okay, there are two steps to it. And don't forget the magnesium must be used in dry ether. So the first thing that you do is you make your Grignard reagent. Okay, so this is, remember what was the formula of Grignard reagent? R Mg Br, correct? Wasn't this the format? So what is my R? CH3 Ca. I'm just writing the simplified structure formula here so that you know what's happening. And then this is my R, and this is magnesium, and this is Br. Give me yes or no if you're okay with the Grignard reagent. So this is my Grignard reagent. So that was my first step. Guys, yes or no if you're okay with this first step. Once I get my first step, my second step is I'm going to take my Grignard reagent and react it with CO2. Okay, so that's my Grignard reagent here, so which I made in the first step. And I'm going to react this with CO2. Now, here's the thing. There is inside steps happening which you don't have to show each and everything. So what happens is when you react this with CO2, there is an intermediate and then you do an acidic hydrolysis. So you basically write everything in one go. So you just say, I'm going to do acidic hydrolysis, right? How do I do acidic hydrolysis? It's basically adding water in the presence. So, sorry. Yeah, plus CO2 followed by acidic hydrolysis. I should not write it this way. I'm just trying to give a best writing style. Hold on. So this is my Grignard reagent. So I'm just going to say react this with CO2 and then H2O followed by H plus followed by what is called as acidic hydrolysis of whatever. So once CO2 reacts with it, whatever compound it forms, we do acidic hydrolysis of it. So that's how I get my CH3CH, CH3, CH2, this whole lot. This whole lot is getting kicked out. Okay, all of that is going to be kicked out there, and I'll get my COOH. That's my COOH which just came in. That's what I wanted. And yes, I don't have to mention, but I get something like a magnesium hydroxybromide. I'm just writing this for your information. You don't have to show this. Okay, so everything gets all kicked out. The OH, the Mg, the Br is all kicked out, is all in one particular compound. But this is what we were interested in. So if you want even to write in a form of a sequence, you could just say this plus magnesium to form this and just make an arrow straight away, write all of that and show that. You don't have to write any secondary products. Okay, on a scale of 0 to 10, tell me if you're okay with the first example which I gave you. How do I react a Grignard reagent with the CO2 to form a carboxylic acid? I'm going to give you one more question for you to work on this. Let me know, just type R for ready if you think you are. So I'm going to give you another question of how to make a carboxylic acid using a Grignard reagent route. Type R for ready if you think you are. So based on the carboxylic acid that I will give you, you have to figure out what Grignard reagent do you need and then what reaction sequence you have to follow. Okay, so let's do example. This was, let's say, example 1. Okay, so let's do example 2. To prepare propanoic acid using a Grignard reagent plus CO2. Okay, so I wanted to use this format. So by the previous example, you understand that this part is going to come from the CO2. So what is the Grignard reagent that you want to use? Where is this part going to come from? Can you suggest? You can write the name, you can write the structure. Don't worry about the type errors. The trick is just put the Br next to it. Look at the previous example. Just put the Br next to it. You got it now? So did you get CH3, CH2, Br? Did you understand that's the bromoalkane? Guys, this is very important for me to know that you're okay here. Everyone is fine. Okay, good. So let's say I want to write the whole thing in one sequence. So okay, so how do I do that? So I'm just going to put that here. So just you can write in this form: magnesium in dry ether. Okay, so what will I get? I will get CH3, CH2, MgBr. We're just following, making a reaction sequence. That's it, schematic sequence. Okay, then what do I do? Who's my reagent? I have to react this with CO2 and followed by H2O slash H plus. I'm doing acidic hydrolysis of the whatever reaction intermediate is formed. So I will get here CH3, CH2. This whole lot is kicked out. This whole lot is kicked out. And I will get here COOH. I got my propanoic acid. Plus the secondary products is there, but which I'm just asking you to not to pay too much attention to it because you will be asked only with respect to sequence there. Okay, give me yes or no if you are comfortable in what happened and you understand this is how it's going to go. Okay, so which means if I ask you to prepare, last question, to let's say I want ethanoic acid, what do you suggest? What do you suggest? Using the same thing. See, I can prepare ethanoic acid from other sources also. But what you are learning here is how do I make it from a Grignard reagent? Guys, don't forget, I can bring this acid from another source. I can take a halogen alkane and do a nucleophilic substitution. I can put a CN inside the nitrile group, and then I can do acidic hydrolysis of the nitrile. I can get my carboxylic. I can come from another way. But the idea here is how do I use a Grignard reagent to get it? That's what we're trying to understand. So using Grignard reagent. Why don't you think of the things required to make ethanoic acid by the time I finish writing? So definitely I need a Grignard reagent and definitely I need the CO2. That's the learning point here. You want to make a carboxylic, you got to have CO2 and you got to have a Grignard reagent. Okay. So you know this comes from CO2. So where is this coming from? So now you know what to do, isn't it? It's so easy. This is going to come from CH3Br. Is that agreed? Give me yes or no. Well done. Well done. So I think now it's easy. Now you can just develop your own schematic diagram. You know how this is going to go. So I have CH3Br. I'm going to react this with magnesium in dry ether. If anybody says why dry ether, because the Grignard reagent reacts very quickly with the water. There's another reaction there, but that's not a part of our discussion. So that's the issue. We don't want water to be present. So I first of all, I need my Grignard reagent to be ready, and it's going to look like this. I have a CH3MgBr, so that's my Grignard reagent, and then I need my CO2. Then we're going to do acidic hydrolysis. Better word is followed by, not then. I don't like that word. So followed by. Okay, there you go. Nice and easy. So this is all kicked out, and then I'm going to get my carboxylic in. There you go. Plus, of course, I'll get all the secondary products which I'm not interested in. Okay, and we are done. Do you have any questions? Give me, if you have no questions, type NQ. If you're okay with examples, you know how to break it up. That's the trick I want you to learn. Where to break, how do I know which Grignard reagent to use? If you're comfortable, let me know if you have no questions. There are 4 different types of reactions. Well, main idea is like you kind of ready. Can we do the second one now? So the first one was reaction with CO2. And now what you learned here is when I do reaction with CO2, I get what is called a carboxylic acid. Okay. Now this is the B part. The B part is a reaction with one particular aldehyde. Reaction with methanol. Only methanol at this point of time. HCHO. It's a carbonyl compound. It's a carbonyl compound. Reaction with methanol to form, now this is what you will memorize, to form a primary alcohol. So if you want a primary alcohol, you want to put the OH at the first position, you have to think of methanol. There is no other. If you work with any other aldehyde, I will tell you what happens very shortly. So if you want to put the OH at the first position, you got to use methanol and a Grignard reagent. That's it. Okay, that's the learning point here. Okay, so just to make sure that you understand, so I have a Grignard reagent here, and I'm going to react this with HCHO. Okay, and of course then followed by the I have to still do the acidic hydrolysis everywhere at the end, and finally when I do all of that, I'm going to get my primary alcohol. So that's the general schematic idea how this is going to go. Okay, ready? Let's do example. Let's say I want you to make preparation of what example can we take? I'll give you one and then we will try to work on some other extra ones. Okay. Preparation of propane 1-ol. Okay, so that looks to be a primary alcohol, which is a CH3CH2 CH2OH. Okay, now assuming that you understood everything what happened here, like who gave the COOH, who gave the reagent, Grignard reagent, can you apply the same logic here? Can you apply the same logic here? Where is this going to come from? I think you got the idea, no? This comes from HCHO. I think you're getting the idea now. And what could be the Grignard reagent I need? What could be the bromoalkane I need? So the bromoalkane that I need will be CH3CH2Br. First of all, guys, give me yes or no if you understand what bromoalkane do I need. So I need the bromoalkane, I need magnesium to form the Grignard reagent. And once I have that, I will then react it with my methanol. Okay, everyone is still following what's happening. So this is how I come to know, okay, I need bromoethane. I need bromoethane. And I'm going to react bromoethane with magnesium in dry ether. And once I do that, I will get my reagent. And once I do that, I need to react this with methanol and then followed by acidic hydrolysis of the reaction intermediate. So all of that is going to be kicked out. All of that is going to be kicked out and it's going to be replaced by the CH2OH. Yes, I will get as usual my secondary product which still continues to be magnesium hydroxybromide everywhere. But then that is not our concern. Okay, so this is propane 1-ol. Is this okay? Is this okay? Okay, tell me yes or no if you are comfortable with this question. I'm going to give you another one to work on. Guys, give me yes or no if you're okay with this question. So I got my primary alcohol. And how do I know it's a primary alcohol? Because the CH2OH, that's the primary alcohol group. Guys, I'm still waiting for your response in the Zoom chat if you're okay on this example. No questions? Okay, good. So I'm going to give you a question for you to work on. See if you are able to very correctly and with confidence you are able to figure out what is the bromoalkane required and how do I know. Okay, so let's look at another example there just to make sure that you are okay. So let's say this is example number 2. I want you to make, let's say, how about butane 1-ol? Okay, hold on. Let's make it something very fancy. 1, 2, 3. How about 3 methyl 1, 2 butane 1-ol? How about this one? Preparation of 3 methyl butane 1-ol. So the first thing you want to do is you want to make sure that the structure that you are going to work on, you correctly open that structure, right? So I want to make the structure of butane 1-ol. So it's a 4-carbon situation. So I know that's the OH and I know that's the CH3. This is a simplified way of the structure formula there, just to give you a very good clarity. Correct? Yes, I can write this as CH3 two times, and then I have a CH, and then I have a CH2, CH2OH. I can do that as well, okay, but any format. But I am opening up this structure because it's easy for you to understand. Okay, even if that's easy for you, and then I can just break this up a bit. Okay, so now you know what bromoalkane do you need, and what is my second reagent, which is the methanol. All reactions are with methanol. Um, Type done if you think you're okay with the reaction. Maybe you can work it out yourself. Could you tell me the name of the bromoalkane that you think you will use? Name of the bromoalkane. I think everyone is comfortable now, right? So I have here, I can even work in the short form. I don't have to open up that, so I can work with this format also. CH3 to CH, and then I have a CH2, CH, and then I have a CH2, and then I have a Br here. Okay, so this is basically 1, 2, 3. So this is one bromo, 2 methyl propane. Is that okay? Is that okay? Because that's carbon number one. This is carbon number one, carbon number two, carbon number three. So bromine is at first position, methyl is at the second position. So one bromo, and we say bromo first because alphabetical sequence. So I'm going to react this first of all with magnesium in dry ether, and this is going to help me to get my Grignard reagent, which should look like this. I have a CH2, and then Mg, and then Br. And once I have that, then I'm just going to follow this with, so who do I react this with? Remember, we are doing the reaction with methanol, which is the first of the aldehyde family. So that's HCHO, and followed by H2O slash H plus, and this is going to give me CH3 2 CH CH2, and then I have the CH2OH. That's the extra which is coming in here, of course, plus the MgOH and Br. Okay, all done. So this is what we have, our 3-methyl. Now, since I have 1, 2, 3, 4, it's like basically a 4-carbon chain. So 3-methyl butane 1 all. Okay, so if you want to open the structures, that's the 4-carbon chain. So that's the OH there, and methyl is at this position. So this basically is the structure here. Okay, I'm waiting for your questions if you have any. Just give me a second, guys. Okay, guys, waiting for you if you have any questions for me. So that's the end of our second set of equations. So the first set was reaction with CO2. The second reaction shown by Grignard reagent is reaction with methanol. We are specifically talking of methanol to form the primary alcohol. So if I want to make a primary alcohol, That's basically how I'm going to do this. Okay, I'm waiting for you to tell me if there is any concern before I move on to my third reaction. Or maybe you can give me a scale of 1 to 10 just to let me know what comfort level you are in for the reactions done so far. Thank you. Good. So everyone is fine. Good, good. Okay, so let's have a look at now. We finished a reaction with CO2. We know how to make a reagent. We know what happens if I react with CO2. I'm going to get a carboxylic acid. Then we know what happens if I react with methanol, specifically methanol. And this is done to make sure that we get a primary alcohol. So any primary alcohol I need, I have to make a Grignard reagent appropriate for that, but react it with methanol. So that's the learning objective here. Two examples we did, and let's have a look at our C part. Okay, this is a reaction with uh, other aldehydes.
Sure.
Yeah, Baba.
The MgOHBr, why do we have to put the OH in brackets? Can't we just put it as like
It's a writing format.
OHMgBr?
It's a writing format I've seen everywhere in the book, I guess. I'll figure out
Oh,
the
okay.
explanation for it. It's just maybe because it's the OH connected to a metal. It's not an organic. It's basically a organometallic compound, as we say. It contains but then there is no carbons there. I'm sorry, disregard that. It's not organometallic, but it's probably the writing format. Let me find out more about it. Okay,
Okay, thank you,
but I'm
sir.
pretty sure there is no specific reason. Reaction with other aldehydes. Now, when I say reaction with other aldehydes, that means other than HCHO. So now comes the other aldehydes like ethanol, propanol, butanol, and so on. Because methanol is only to get primary alcohol. Okay, so if you work with other aldehydes, you will now get secondary alcohol. So this is the story. So if you want primary alcohols, you only have to use methanol. If you use any other aldehyde, ethanol, propanol, butanol, you will end up getting a secondary alcohol. So first of all, is this point very, very clear? So, it's a simple, very, very straightforward sentence. So how do I know if I have to make a primary, I use ethanol. If I want to make secondary, I use any other aldehyde other than methanol. If I want a carboxylic, I'm going to use a CO2, and then accordingly you'll figure out the Grignard reagent. That's the general. I think you're getting the drift how this is going. Okay, so let's give an example of this scenario. Okay, so let's say example preparation. Okay, preparation of, let's say, pentane 2-ol. Now pentane 2-ol happens to be a secondary alcohol, correct? So that's basically CH3, CH2, CH2, CHOH, CH3, 1, 2, 3, 4, 5. Okay, good. So that's basically pentane 2-ol. So I see there is a secondary alcohol there, right? So now what happens? This secondary alcohol, this entire CHOH, this entire bit, okay, this bit has to come from an aldehyde. Now I can clearly see there are two carbons here, right? So that's how I come to know, because since, let me write it, since two carbons needed, that's the reason why. So my aldehyde has to be CH3CHO, which is your ethanol. It's a two carbon aldehyde. Did you understand how do I figure my aldehyde out? Because I look at CHOH and then I look at how many carbons are on the right side. I see there's a total of two carbons involved, which means my aldehyde is two carbons. If I had three carbons, I would have taken propanol. If there were four carbons, I would have taken butanol. Guys, give me yes or no. You get the idea how this is going. And then this is coming from the bromoalkane, right? So this is coming from uh, bromoalkane. So which bromoalkane do I need then? So I need a 3-carbon bromoalkane. So it's very easy. I just copy the whole thing as it is and I just stick a Br to it and we're done. So that I need 1 bromopropane, right? Everyone is still comfortable? So how does this sequence work? So I need my, let's say I need my bromoalkane, and I'm going to react this with magnesium in dry ether. So I will get here CH3, CH2, CH2, MgBr, and that's my Grignard reagent, correct? And then I have, what do I need? I need ethanol. So I need CH3CHO ethanol followed by, I still need to do my acidic hydrolysis everywhere, followed by that, and eventually that all is going to go, that's all is going to be kicked out, and I will get CH3CH2CH2, that's all coming from there, and I'm just going to add use another pen there just to, and I'm going to get CHOH, CH3, and we're done. Okay, the book and all everything just says this. They don't actually even talk about the secondary products. Okay, but we're just understanding the format of writing again still goes that way. Okay, okay. Questions at this point of time?
Sir, why do we need to add Mg? Can't we just like react the CH3, CH2, CH2Br directly with the CH3, CHO?
Okay, see, we can make this compound by different ways. Okay, I can make a 3-carbon into a 5-carbon. I can connect using maybe convert this into an aldehyde or a ketone, do a carbonyl reaction with HCN. There are routes available, but the point that you are studying is how do I use a Grignard reagent to make it? I'm not saying this is the only way how to make it. Get the idea? So how do you
But
deduce?
like, what's the point? What's the point of a Grignard reagent if we can just like directly react it?
No, directly react with who? Once again, can you just repeat what you said? React with?
Like, why do we need the Grignard reagent if we can just directly react the bromoalkane with the CH3CHO?
Oh, you can't. Aldehydes don't react with halogen alkanes. Aldehydes
Can we
don't
not
react with
like?
halogen alkanes. Aldehydes can undergo oxidation reaction using acidified potassium dichromate. They can undergo reduction reaction using lithium aluminum hydride. They can go nucleophilic addition reaction using HCN and KCN catalyst. These are the reactions of aldehyde. They
Oh,
cannot react
okay.
with halogen alkane. Now I got what you're saying. I mean, you cannot take ethanol and react with bromopropane. That's going to be no reaction. So you use a Grignard reagent route to make that happen, to connect that 2-carbon bit, the CHOH CH3 bit. Make sense?
Yeah, thank you, sir.
Yeah. That's the issue. Okay, but I can do other reaction. In fact, remember the organic synthesis route. It's not that I have to use Grignard reagent everywhere. This is a situation where you will be asked to use one of these to figure out to reach from point A to point B. Then what are you going to do? That's what I'm teaching. Okay, makes sense? Okay, let's do another one. So this was, let's say, pentane 2-ol. Okay, let's do another example using Grignard reagent. Remember, that's the idea here. So, for example, let's quickly look at one more example. How about if I give you, let's say, preparation of. Now, I can make butane 2-ol from different ways. Preparation of butane 2-ol. Now, if you're going to say What are the different ways? I mean, I can work with butanol. I can do reduction of butanol. I can get butane to all from there. I can work with the 2-chlorobutane, convert the 2-chlorobutane into butane to all. We can do all of that. But the point is preparation of butane to all using, this is what I want you to focus all the time. So using this, how do you get? Okay, so that's the challenge. So how do I get butane to all, which clearly is a secondary alcohol? Now, because it's a secondary alcohol, I have to use an aldehyde which is other than methanol, correct? Because butane to all is this. This is butane to all. So now I think it's easy that this bit and this bit. Guys, can you work it out? Kathy, what do you think? So now you know what to do. Why don't you think for a few seconds and figure out the reactants what you need, and I think we can just finish this very quickly. What do you think? So I need, and what aldehyde do I need? I have a 2-carbon situation here, so I need, for example, this could be hexane triol. Then I need a 3-carbon situation. In this point of time, I need CH3CHO, and I need CH3CH2Br, and that's it. Well done, Kathy. That's it. And once you figure that out, and the rest is all easy. Just CH3CH2Br. You start with bromo ethane, and then you do a reaction with magnesium in dry ether. You switch this to a Grignard reagent there, so that changes into CH3 CH2 magnesium bromide, and then you do the what you say you're going to react this with CH3CHO, and then followed by H2O slash H plus. So this is all going to go out. So I have here CH3CH2, and the CHOH and the CH3 is going to come from there. Okay, so that part is coming in from the ethanol, and that's it. All right, tell me if everything is very clear. Guys, is everyone very clear? Are we okay with the third set of equation? It's easy now, right? The first one was with the carboxylic acid, sorry, with CO2 to form the carboxylic acid. The second was with methanol specifically to form the primary alcohol. The third one is with other aldehydes. Okay, very quickly, if I ask you to make hexane triol, which aldehyde will you take? Can you mention in the Zoom chat? If I want you to make hexane triol, which is at the third position, which aldehyde will you take now? To make hexane triol, which aldehyde will you take? Very good. So you will take propanol, 3-carbon aldehyde, correct? I'm not writing the equation, but just want to be sure. For example, to prepare hexane 3-ol. Now hexane 3-ol is going to be like this. So this is hexane 3-ol. So that means now you understand this part here has to come from an aldehyde, right? So this part is going to come from ethanol, CH3, CH2, CHO, 3-carbon aldehyde, 3-carbon aldehyde. Does that make sense now? And then this part here, bromoalkane. This is going to come from which bromoalkane? So CH3, CH2Br. So that's the bromoalkane required. Khalas, then you know what to do. Take the bromoalkane, react with magnesium, get the Grignard reagent, react with propanol. Finish. You're done. Easy. How do you feel on these equations now? And directly, the point that we were discussing earlier, directly, I cannot take bromoethane, I cannot react it with propanol because there is no direct reaction between halogen alkane and aldehyde. Don't forget, aldehydes can do oxidation, they can do reduction, they can do nucleophilic addition, but they cannot do a reaction with the halogen alkane. That is not possible. So that's why we are using this particular route. So we are done with the third. Let's have a look at the final one, which is the D part. So this is reaction with ketone. So we can even make the Grignard reagent react with ketone to form, and this is how we get tertiary alcohols. So tertiary alcohols. Remember, how do we get tertiary alcohol? So this is carbon with OH. Okay, this is R, this is R dash, this is R double dash. I'm just assuming that R dash and R double dash, they're all different R group, different alkyl groups. I can put them same also, I can put them different also. But what is important, that the carbon which has the OH has got no hydrogen. So this is how we come to know this is the tertiary alcohol. So now is the good time for you to summarize. If you want carboxylic acid, react with CO2. If you want primary alcohol, react with methanol. If you want secondary alcohol, react with any other aldehyde, ethanol, propanol, butanol, whatever. And if you want a tertiary alcohol, react with the ketone. So you got to memorize them. Okay? And reactions are pretty straightforward. So let's do some reaction there. So let's say, example, to prepare. So let's say I want to prepare 2-methyl 2-hydroxy propane. 2-methyl 2-hydroxy propane, or in fact, the other variation, no, hold on. It should finish the name with all. So 2-methyl propane 2-all. That's the correct. Okay. 2-methyl propane 2-all. So basically what's happening now, I have a propane, and let's say this is the OH group there, and that's the methyl group here, that's the methyl group here, that's the methyl group here. Yes, you can also write this as there are 3 CH3s. I can put them same, I can put them separate. It doesn't matter. Okay, I could have put here CH3, I could have put here C2H5, I could have put here C3H7, I could have changed the R group, but that's not the issue here. The issue is, okay, how do I figure out my reagent? Like, what is my bromoalkane, and how do I work this out? And what is my ketone that I need? If you look carefully, I have like a 4-carbon situation, right? Everything I have a 4-carbon situation. So what do I need here? Which ketone? So if I have here, which ketone do you think? Anyone wants to try? Yes, C should be the start. Absolutely correct. But which? But I know that is, once I have the Grignard reagent, I need a ketone. So can you tell me which ketone do I need and which bromoalkane do I need? Anyone wants to suggest? Which bromoalkane do I need? Because it's a 4-carbon situation total, correct? The smallest ketone is 3 carbon. Yes or no? Total 4 carbons are there. Okay. Now you know the smallest ketone. The smallest ketone is propanol, correct? CH3COCH3. So I need propanol and I need 1 carbon as my bromo. Very good. Now I got the idea perfectly correct. So I need CH3Br. I need 1 carbon bromoalkane. The 3 carbon, the ketone that I need is propanol. I need propanol because it's 4 carbon. So out of the 4 carbons, 3 carbon will come from the ketone because I cannot get a ketone smaller than this. Ketone is minimum 3 carbons. Okay. So that means my bromoalkane has to be the CH3Br. Okay, so that's the CH3Br. So now it's easy. You just have to finish off the reactions then. So I'm going to start with CH3Br and first of all convert this into my Grignard reagent. So that changes into CH3MgBr, and now I need my ketone. So that is my CH3COCH3, but then followed by acidic hydrolysis. So now this MgBr is going to get kicked out, and this ketone bit, that's the one who's going to give me all the remaining stuff. Okay, I'm just writing it this way, or maybe let me write the normal way so it's easy. So let's say I have a CH3, and then I have that OH there, and then there's a CH3 there, and there's a CH3 there. That's ultimately what I have. Okay, of course I must, in fact the correct writing style is this. I should write it like this. That's my tertiary alcohol. Okay, so first of all, is everyone okay with this? You understand how to work with the ketone. Just look at the ketone, how many you need, and accordingly just do it out. Okay, so well, the thing is that's the end of our this thing. But can I just give you some normal general conversion questions? We still have a couple of minutes, and if you're not too tired. Sorry, is it that C? Normally, the way of writing is that we write it this way, Kathy. I mean, we write the COH later. We write the CH3 first and then the COH. Okay, this is usually you will not see this in the textbook, this format. Okay, this is the
Didn't,
generalized.
didn't we used to didn't we used to write it like that? Like we have the brackets after the
I
thing
can't
that
hear
it
you.
is.
Okay, speak a bit louder.
Didn't we used to have it that the C is before the CH3
Now, if you notice here, when I did the secondary alcohols also, we wrote the CH3s like that. You see this? Even in the your textbooks is going to go this way. It's basically just the two
Okay.
CH3s and then the CH. It's perfectly fine. I'm not saying you're wrong if you write it that way. I'm not saying it's wrong if you do this way. A carbon connected to three and then OH. Basically, you wouldn't see this in the textbook as well because the OH is connected to the carbon. Now you see the way you wrote it. It's like the OH and the carbon are showing like they're not together. So that's why it's much better to write it that way to show that the OH is actually connected to the carbon and it's also connected to the 3CH3. So that this way is a little bit more kind of gives correct way information compared to the other way. Does that make sense what I'm saying? I don't know. I hope that makes sense. I just want like you should highlight that
Yeah.
OH is connected to the carbon. So that's why we did that. Okay. Okay, so that's about it. And well, there, I have so many more questions for you. But maybe what I can do is maybe I'll use them as a warm-up question when I see you in your next class. Finally, face to face. I think. And but I think we are almost done with this lesson. So I think by next class I'm going to finish this chapter. So that's a good news for all of you. And then we will discuss our plans for the remaining sessions. Okay, just give me a minute. If now, what about if you have any doubts, anything so far for this what I did today? Please let me know. I'm still here. And for the rest of you, if you have nothing, no doubts, you can start leaving, and I will send all the information on your WhatsApp soon in the next few minutes.